Okay, as promised, here's the mechanism quiz. It's actually not a mechanism quiz, it's going to be a reaction coordinate diagram quiz, I decided. But I'm going to talk to you about it in this video. In this animation I'm clicking through, that's going to be available for you to click through as well and to practice, get ready for the quiz. Alright, so we're looking at the conjugated Diene Hydrobromination reaction. You could see we've got a Diene here, conjugated, double bond, single bond, double bond. HBr, and this reaction, if you run it at 0 degrees Celsius, it's different than if you run it at 40 degrees Celsius. But we will get these products, a mono-substituted pair of enantiomers, a di-substituted cis product, a di-substituted trans. All right, so how do you prepare? Watch the lecture from today, the video I put up from 316. So if you go to our website, lecture videos, boom, there it is. Watch this one. At the end of that video, you'll see this, this mechanism worked out for you. And then watch and practice the curved arrow mechanism from that. Yep. Click through the following slides that I'm clicking through now and to understand why temperature can change this reaction from being under kinetic control to being under thermodynamic control. Read over the energy versus reaction coordinate diagram that you're going to see in this slideshow. Your quiz will be to make that diagram, this diagram. So you'll see that. And the last slide of this animation has a blank diagram for you to fill out to practice. All right, here we go. Conjugated Diene Hydrobromination extra credit quiz. There's the mono-substituted enantiomers. These two are both di-substituted, one being cis or Z and the other trans or E. So when you run this reaction at 0 degrees Celsius, it turns out the mono-substituted enantiomers are your major products, the two of them. And these two are minor. And that's actually the fastest product form. So what do you think this one's under? Kinetic or thermodynamic? When it's cool, it's under kinetic control. And when we learned about kinetic and thermodynamic control, we did say that usually they're cooler temperatures. That's nice. Now, if you run the reaction at 40 degrees Celsius, you wind up with this as your major product. And what's special about that? You got it. It's the lowest energy product. It's the trans one versus the cis. It's di-sub versus monosub. Lowest energy product in this reaction happens to be under thermodynamic control at 40 degrees Celsius. So that one you'll make second most, and this one you'll make the least of. So this product, when it's formed, the reaction, it's reversible, but it's hard for it to get back because it's so low in energy. So here's the reaction coordinate diagram. This is like a blank version of it that I'm going to click through and fill in, and that's what you're going to be doing for the quiz. So here we go. Is it kinetic or thermodynamic control? So you start with the Diene and the HBr. First it protonates and it makes the carbocation, and the bromide should be on there. We'll see if it shows up. And that carbocation has resonance. And you can see the resonance that way too. There's my bromide. So a lot of my students in the past would think this resonance structure and this resonance structures deserve different lines of energy, but no, remember, this is one molecule. This is the same molecule, slightly different conformation, probably would be tad higher in energy or something, but let's just keep it all the same. Okay, so we got that, and then the bromide can go in and hit at these different carbons. Oh, but first off, let's look at this guy. This is a resonance hybrid of it. You can see I put more positive on the secondary carbon and less on the primary. Turns out that's the case. It's kind of not intuitive to predict that, but that's the way it works. It's similar to when epoxides get attacked at the more hindered side, remember? So yep, that's more positive there, less positive there, and you can think of it as, oh, this is secondary. It can get donation from this methyl to help it be more positive, but wouldn't that make it less positive? I'm not sure how you want to think of it, but think secondary, more positive, primary, less positive. Okay, so now we make the secondary bromide here, racemic mixture with the monosubstituted alkene if, yep, there we go. And then we'll make the cis or Z alkene, lower in energy, and then the lowest energy is the trans or E. And now let's look at the curves for these. So you have a particular activation energy for this one, and then That would be transition state 2. Let's look at the next one. How did I draw that one out? Did you notice something? I made that activation energy higher, huh? And so it looks like this will be the faster product to form. And then the last one, I'm showing its activation energy to be about the same. So there you see what I was showing you on the last slide. This is your major product under kinetic control because it has a lower activation energy. It can form fastest. All right, let's look at the transition states. The first one, the bromide's going to be coming into that carbon there. Oh, wait. Oh, no, this is when you're first making the carbocation. So the HBr is protonating the alkene, making the secondary carbocation, not the primary. And it's exothermic or endothermic, so it looks more like the products. So I have the H almost completely on the carbon and the HBr bond just about broken. And I get my positive charge. Oh, wait a minute. I need a delta plus there too, huh? Yep. Darn it. Okay, I don't want to remake this video, but there's a delta plus here too. All right, and then the next transition state for the faster form product, you can see the bromides coming into this carbon, and this is the key. That carbon has more of a positive charge, and this carbon has less of a positive charge. So what do you think? Do you think the bromide is going to be more attracted and react faster at the positive carbon, or the less positive charge? More positive or less positive? So our rationale is that this more positive carbon will attract the bromide more, and it will react faster. Now you might think steric hindrance. This is more steric hindrance than this has more steric hindrance than that, but the bromide is just a single atom and it's polarizable. So I don't think steric hindrance plays a big role in it as a nucleophile. Next up, we got this one where the bromide will be coming into the less positive carbon there. And finally, this one, the bromide's coming in less positive carbon, but you're going to make the cis alkene. All right, so that's the lowest energy, fastest to form product. This is, lowest activation energy, fastest to form product here. Lowest energy stuck in a thermodynamic whole product there, and at 0 degrees Celsius, the reactions are not very reversible. So imagine if you have a cooler temperature, you form this right here, and then you don't have enough energy to get out. And you're like, oh, I get stuck right there. And then when these form, they're less likely to form because there's not as much activation energy available in a cooler reaction. So they don't form as much, but when they do, they're stuck. So none of these are very reversible. But this one's formed fastest, so once it's formed, it's done. It can't go back. So you get that as your major product. And so the fastest product formed is major, this one. So when we run the reaction hotter, now you have enough energy to come back out to reverse the reaction. Isn't that cool? And if you can reverse the reaction, you can reverse this reaction. You can reverse this one, but this one's the hardest to reverse. So reactions are reversible. Lowest energy product, least reversible though, and that's the major product. So that's the reason why that would be the major product. And now for you guys, you're going to do this for the quiz. You're going to fill in everything that's missing. The lines, the blank lines, this or that, temperature. And so this is what your quiz will look like. And take your time, do a good job on it, get the extra credit. All right, thanks for listening.